Okay. Last day, we talked about protecting the border between the U.S. and Canada with a large metal detector, and we found that it was trivial to make a magnet detector. That we just had a coil of wire around a door frame, and whenever a magnet came close or away from that coil, we generated one of these induced, by induced I mean magical, can't see the battery that causes it, current. We found that we could actually make this thing detect metal if we could first turn that metal into a magnet. And one way to do that is to hook a real magnet to it. Don't want to get anywhere close to that. Bring the lecture down. And notice, Kane, that we put the battery on the far side from you today. Now, if I hook that battery to this first coil, now whenever something metal goes through it, it becomes magnetized, and then the magnet detector picks it up. Okay? So now we need two coils. Now, in truth, the magnet detector, the metal detector down at the airport, does not work on DC current. It works on AC current. And so don't be trying to slowly walk through that with your guns and say, well, Greg told me I could get on the plane. It's not going to work. Okay. Yes? What happens if it's like insulated somehow? You wrap in a bunch of rubber. Okay, good question. If I coat myself in spandex, okay? No. Okay, so you got some big coating around you. First of all, you got to trust that those guys running the machine are not real bright, you know. Okay, the next. Yeah. Chances are you're going to end up with the full body search there. But the magnetic field is not going to be affected by some sort of a coating like rubber. Okay? Now remember, when we put a coating of aluminum foil around something, we were able to get rid of electric fields. And if this thing were picking up electric field lines, then that might work. But with magnetic fields, there are some materials that shield out magnetic fields, but you're not going to wear that to the airport. Okay. The key to understanding Lenz's law is having a firm grasp of what we mean by magnetic flux, represented by this scary symbol. And by firm grasp of this concept, what I really mean is, can you see just how darn trivial it is? Okay? Magnetic flux is nothing more or less than the number of B field lines going through the loop, any loop. Okay? When I talk about the flux through any loop, it's just how many B field lines are going through it. Now remember, those B field lines are a representation. It's a picture we paint for ourselves to try to visualize what the B field looks like everywhere. It turns out that they are downright physical in this case, not just a representation. Now, the direction of that magnetic flux we often take to be the direction of the B field lines themselves. Now, in truth, flux is not a vector. It's just easier to think of it as having direction. And we'll talk about that more in a little bit. What's really critical is recognizing that there are two different flavors of magnetic flux. And we have to keep these two flavors distinct in every problem. There is the external flux, which is caused by everything except the loop. And then there's the induced flux. The induced flux is caused by this magical current that suddenly starts flowing as a result of what we're doing with the external flux. Okay, so the two flavors, one's caused by everything except the loop, the other one's caused by the current in the loop. Okay? Questions, please, folks, interrupt me if you've got questions on this material. We had a tutorial on it this week. My feedback back from some of my spies is that it wasn't the rich, rewarding experience that we would have hoped for everyone. Okay? Not everyone felt uplifted. So what we're going to try to do today is make up for that and make sure that you get your money's worth. Faraday's law, we decided, looked like this, where this EMF does not, I repeat, does not stand for external magnetic flux. Does not. What does it stand for, EMF? Battery. Thank you very much, Hope. I was expecting people to say electromotive force, but in truth, it represents a battery. It's not a force at all, it's a voltage. And it's unfortunate that it was named electromotive force. It wasn't my fault. It's a battery that drives this imaginary current, or not imaginary, just invisible. We can't see what's causing it. This part on the right tells me how quickly I'm changing the number of external field lines, the external flux, through one loop. And then I have to multiply that by how many loops I actually have in my coil. Because every time I put one more field line through the coil, it's going through each of those loops of the coil and needs to be counted each time. Now it's this minus sign that we've come here today to talk about, and your tutorial was about this minus sign. We call that minus sign Lenz's Law. And what it should represent to you is fight. Okay? Whatever's going on here, the battery's going to be set up in the opposite direction. Okay? Whatever change is going on here, the battery is going to fight it. That's what that minus sign means, is fight. It's Lenz's law, and it just tells me that the induced magnetic flux through the loop is always going to fight the change in the external magnetic flux. There's the two flavors. The induced flux always fights not the external flux, but the change in the external flux. The most important words up there are change in. Okay? And we're going to develop this idea with a whole lot of examples over and over and over again. But I'm going to start, let me put that back up. I'm going to start with my favorite demo of all time. This is my favorite demo because it's going to make me filthy rich, whereas now I'm only filthy. Eventually, I'm going to be filthy rich. What I have here is just a simple copper tube, okay? And it's important that it be copper because copper, as it turns out, is not magnetic. I've got here a little magnet. You can see it's a fairly strong magnet. But copper is a non-magnetic material, and so it just drops right off. It doesn't stick at all. Now, what I'm going to do is I'm going to take, this is not a magnet, this is just a piece of steel, just an ordinary piece of slug of steel. It also doesn't stick to copper. And I'm going to drop this through the tube. And I'd like you to time it. Who's got a stopwatch? Okay, Sarah, none? One of them fancy watches. Okay, you ready to do this for us, Kim?
Yeah, I'm fine.
Okay, I'll say start, and when you'll hear the ding, just stop it. 1, 2, 3, go. Okay, how many seconds was that? 0.82. Okay, let's do it the old-fashioned way. 1 Mississippi, 2 Mississippi, 1 Mississippi. Okay? It takes 1 Mississippi to get through there. Now, folks, this copper is not magnetic. Magnets don't stick to the copper. When I drop this magnet down here, Is it going to take 1 second, more than 1 second, or less than 1 second? Talk to your neighbor. I remind you folks, more. I remind you, magnets don't stick to copper. More. Okay, I'll show you just how wrong you are. Okay, we go 1 Mississippi. Okay, 1 second. Now, magnets don't stick to copper. And I wish we had time for everyone to come up here one at a time and just look down this tube while this thing drops. It's not stuck there. It's just hovering. It just floats. Slow motion, suspended animation. It's about here now, just floating and out. It's the most beautiful thing. So easily amused. What's causing it? Remember, magnets don't stick to copper. I'm sorry? Well, Trevor's going right to Lenz's Law. That's what the lecture is on today. Tell me more. What is it about this copper tube that is invoking Lenz's Law? How is it slowing that magnet down? It's creating a current. Thank you, Russ. And that current, remember folks, whenever I take a bar magnet and bring it close to a loop, that generates a current. Well, this tube represents a loop of copper, kind of like this loop of copper. Whenever a magnet comes towards it or away from it, I generate electric current. It's the induced current, the magical, don't see the battery, what causes it current. And if I drop that magnet such that the North Pole is facing down, this induced current going around sets up a magnetic field to fight it. That means down on the bottom part of the tube, the current has to be going around this way. Why? Because by right-hand rule number 3, current going around this way would set up a little magnetic field with the North Pole up. Kind of like that. Whoops. And so that's going to fight it as it comes down. Likewise, whenever I take a magnet away from a current or a copper loop, away from it, that also generates a current. And up there, the current is going to be the opposite direction. Why? So that it can fight that flow, that fall of the permanent magnet. Now I want the North Pole to be facing this South Pole, to pull on it as it goes down, to slow it down. Now, why should nature work like this? Why not the reverse? Why wouldn't these be just exactly opposite, where this one's flipped to pull it faster and this one's flipped to push it faster? That would be incredible, because then I could hold it like this, just give it a little tap, and suddenly it gains all this energy. This is a bazooka, folks. Okay? What we're talking about here, we've called it Lenz's Law, but in reality, it's an old principle we've covered before, and that is conservation of energy. No free lunch. When I drop this magnet down here, if I just drop something regularly, it speeds up. As it drops, I lose potential energy, gravitational potential energy, but I gain kinetic energy. Well, here, I'm losing potential energy. It's getting lower, closer to the Earth, but it's not speeding up. It's just gradually going down here. Where's that energy going? Oh, dang, I wasn't supposed to drop that. It's going into this flow of electricity, this current that's surging through the bottom and the top of the copper tube. That's going to heat up the tube. And essentially, that energy has to come from somewhere. I don't get it free. It comes from the fact that I'm losing potential energy and not putting it into kinetic energy. Now, I told you that was going to make me rich. How's that going to make me rich? Someday, I'm going to make a tube that's not that big, but as big around as this room and 10 stories tall. And I'm going to have a suit with hundreds of those little magnets all over it. And what am I going to do with that suit? No, I'm not. I'm going to charge you $50 a piece to put on that suit and jump. And you'll just coast all the way down, do flips, just glide. And the reason it's worth $50 is because my brother's going to have to test that every morning. Now imagine if someone came in the night with a very fine saw blade and cut a slice right down one side of the tube. My brother puts on the suit, jumps in, and like a rock. Yeah, because now we can't generate those currents around to fight the motion. Okay, I love that demo. Now, what we're going to do is we're going to take this principle of conservation of energy that says that this induced current will always fight my motion. If I bring this North Pole towards the loop, it's going to set up a current that's going to fight me, North Pole to North Pole. If I try to take this North Pole away from the loop, it's going to set up a current that's going to fight me, North Pole to South Pole. Okay? It will always make my life harder. We're going to use that to try to develop Lenz's law. Suppose I bring this magnet, North Pole first, down on a copper loop. What direction does the induced magnet have to be to point, to push back on that? What direction would the North Pole on that induced magnet be, up or down? It's got to be up like that, okay? Now, there's not really a magnet there. What really happens is an induced current flows around either this way or that way. Which way would it be? Yeah, I got to use right-hand rule number 3, and it's going to be counterclockwise, like that. Okay, now look at the two flavors. Look at the two flavors of flux at the center of that loop, okay? Both flavors. I got the external and I got the induced flux. Okay, first of all, the external flux is due to what? Due to the magnet up there. And that flux is going to point down in the loop or up in the loop? Down in the loop, away from that North Pole. The induced flux, we decided, was going to be up like that. Now watch what happens as that magnet gets closer. The external flux gets longer and longer. The vector gets longer and longer, meaning the magnitude, the number of field lines going through the loop gets bigger and bigger. Now we can think of these field lines as coming out of the north and then kind of spreading out. And so the closer I get the end of that magnet to the loop, the more of those field lines are going to actually pass through the loop. Now, what if I'm moving the loop or the magnet the other way? Now, the magnet that has to be induced in that loop to fight my motion is going to have what pointing up? A south pole to fight it. And that means the current that's induced that shows up without a battery has to be going clockwise, again by right-hand rule number 3. Now again, let's look at the two flavors of flux. The external flux coming out of the battery is pointing down, and the induced flux is also down. And watch what happens to the external flux as I take it away. Okay. Hold on, folks. We are that close to getting to the punchline. Okay? Here it is. These two cases, the one on the left where the North Pole's coming down, I start with a magnetic flux down that's kind of wimpy, and I end up with a great big magnetic flux down. What change do I have to add to this little vector down to get a big vector down? I have to add something down. And we found that the induced flux in that case was up. In this other case, I start out with a whole lot of flux down. As I move that bar magnet up, I still have flux down, but it's weak, not as many field lines. I then ask myself, what change do I have to add to this long vector to get this short vector? I have to add something up. And in this case, we find the induced flux is down. This is the point that I'm trying to make. This induced flux is always in the opposite direction of the change. Always in the opposite direction of the change. Now, I've heard people say, well, let's see. The magnet's given the external flux, and the magnet's given an external flux down, so the induced flux has to be up. Why should that get 0 points on a test? Why should that get less than 0? Why should that get minus 25? It's just not true. It's sick and wrong. I mean, in this case, the induced flux is in the opposite direction of the external flux. But in this case, the induced flux is in the same direction as the external flux. It's the change that matters. The change is what gets fought by this induced flux. Okay, there's the grand key. The induced flux, the blue, seeks to counteract the change, the purple. Would you check that your neighbor is on the bus? This is the last place we want to lose people. Are you guys on the bus? Okay.
Is the bus almost there?
We're there. We're just going to practice now. Okay. The question was just asked, is the bus almost there? The bus has arrived. This is it. What we're going to do now is practice this until we are sick and tired of it, okay? Well, I'm already there. Wait a minute. Can I leave now, Greg? I'm sick and tired. Let's practice it with some examples that can be worked more than one way. In truth, there's 3 ways to find the direction of this induced current. We found the direction of the induced current using the magnetic force with right-hand rule number 1 last day on Wednesday. But that requires that there be relative motion between the external source of magnetic field and the loop. We also found this principle of conservation of energy. We found that it always sets up that induced current to fight me, to make it harder for me to move the magnet. And then the third way is this technique that we just learned, where the induced flux always is in the opposite direction as the change in external flux. Let's use 2 of those methods here. First of all, in this case, where the south pole is being brought close to this coil, this solenoid, and I've just taken the ends of the solenoid and welded them together. And the question is, when I bring this south pole towards this solenoid, I'm going to induce a current in the solenoid. Is that going to cause current to flow this way in this wire or that way in this wire? To the right, to the left? Okay, first of all, let's do it with this approach that says I have to fight it all the way. As I bring this south pole in, this is going to turn into a magnet that's going to fight my motion. So this end of the solenoid is going to turn into what pole? A south pole. South pole against a south pole gives me fight. So there's my south pole. What direction does the current have to flow in this solenoid to give me a north pole that way? Well, again, I use right-hand rule number 3. The current has to come down the front of that solenoid and up the back. If it's coming down the front of that solenoid, it's coming down this wire right here, through this wire there to the right, and then up the back. Okay? That's the answer. Now let's do it the other way. When I do it the other way, I have to be very careful to distinguish between the two flavors of flux. I have to keep the external flux separate from the induced flux. The external flux is due to what? Due to the magnet. And the external flux, you know, this magnet's sending field lines out the north and in the south. Everywhere in the room I got a magnetic field due to this magnet. But I don't care about it everywhere. I care about it over here. What direction do the field lines point over here due to that magnet? Towards the south pole here. Okay? So the field lines due to that magnet over at the location of the solenoid are to the left. Like that. And as that magnet gets closer, what's going to happen to that external flux? It's going to get bigger. More field lines are going to be passing through the solenoid. The change that I have to add to this small flux to the left to get a large flux to the left is something to the left. That change is what will be fought by the induced flux. So the induced flux has to be that way. That means to get induced flux that way, I have to make current flow down the front, across that wire to the right. Same answer we got the other method. Greg, if it works both ways, why don't you just let me do it the easy way with the south pole against the south pole? Because we have a host of problems where there is no relative motion. The south pole technique is not going to work. This technique of looking at the change in external flux will never, ever fail you. You can use this for every single Lenz's Law problem. And that's why that's the technique I want you to adopt as your plan A. Okay? As your plan A. Let's practice it with a different scenario. Now the North Pole is leaving that solenoid. Don't do it with this, I gotta fight it, energy argument. Do it the way that always works. Do it with the change in external flux. With your neighbor, which direction is the current going to flow in this wire right here? With your neighbor, figure it out. Okay, let's vote. The current that's induced either goes to the left or to the right in this wire down here. Those who say to the left, those who say to the right. Okay, we got some of both. First of all, we have to look at the external flux. By external, we mean due to the bar magnet. And field lines come out of the north pole of a bar magnet, so they're going to be pointing to the left. As that bar magnet moves further away, there will be fewer field lines passing through the solenoid. The magnitude of that external flux decreases, but is still to the left. What change do I have to add to this long vector to turn it into a short vector? I have to add something to the right. And that means the induced flux has to be to the left. It has to fight the change vector. And in order to get an induced flux to go to the left, I have to have my current go up the front of the solenoid and down the back. If it goes up the front of the solenoid, it has to go up this wire here, which means it has to go across this wire to the left. The answer is to the left. Check that your neighbor's on the bus, please. The wheels on the bus go round and round, round and round, round and round. Okay, questions on this? Okay, here's an example. Here's an example where there is no relative motion. The whole idea of fighting North Pole against North Pole or South Pole against South Pole is not going to work. This is the case where I just have two coils sitting next to each other, and I put current through the one coil, and that's going to cause an induced current in the other. So the question is, when I close this switch with the battery oriented this way, am I going to send current, induced current in this second solenoid with the current going to the right or to the left in this little hangy down loop? Okay, talk to your neighbor about that. See if your neighbor can do this one.
I don't know.
Not clear what we're doing?
We're not sure which way the current's going to flow.
Okay, folks. When I close the switch here, what direction is the current going to flow in this? Yeah, from the positive terminal of the battery, up the front, around and around and around, and back to the negative terminal of the battery. So when I close this switch, this is going to be the north pole of this solenoid right over there. Okay, now with your neighbor, see if you can figure it out. Okay, time to vote. Those who say the current's going to go through this wire going to the left, going to the right. I fell off the bus. Okay. Let's do it together. When the switch is open, there is no magnetic field due to that solenoid on the left at the location of the right. There's actually no magnetic field anywhere except the Earth's magnetic field. And so I would represent that with just a dot. There's no vector, not to the left, not to the right. When I close that switch, that turns that solenoid on the left into a bar magnet with a north pole on the left, again by right-hand rule number 3. That's going to cause an external flux over here. What direction? To the left, towards the South Pole. Okay? Keep it straight. External means everything due to things other than the loop that's going to get the magic or the invisible current showing up. So that external flux is now going to be to the left. What do I have to add to nothing to get something to the left? I got to add something to the left. It's that change vector that the induced flux will fight. The induced flux has to be that way. And that means the current that will create that induced flux has to come down the front and to the right there. Are there questions on that? Okay. Yes?
But it's essentially that.
What's that?
That demo you have is essentially what's up.
It's exactly the same.
But after it initially turns on, then it goes back to zero.
Yes, okay. the change in flux is only happening right when I close the switch. Okay? I'm going from no field lines through this second loop to some field lines. But after that first initial half a second, I'm just going from some field lines to some field lines, the same number of field lines. And now the change in flux is 0, and it suddenly, the induced current goes away. Until I open the switch. And then I get induced current in the opposite direction. Let's see why it would be in the opposite direction. Remember, when I closed the switch, it went to the right. Now let's open the switch. Now I'm going from external field to the left. When I open the switch, suddenly it goes away, and I've got nothing. What do I have to add to something to the left to get nothing? I've got to add something to the right. That's the change that the induced flux will fight. And in order to fight, or in order to produce that induced flux, I would have to go, current would have to go up the front of the solenoid, which would mean to the left in that wire. The opposite of what was before. Okay, everyone happy with that? Yes?
What if, like on that one you had your north pole and the south pole, what if you had two like poles together? I mean, how did you know that?
This one doesn't have a north or a south pole because it doesn't have a battery.
Okay.
Until I make this connection here, there's no current over there.
Okay, so closing that connection causes that to happen.
Yes. Yep. Okay, here's a similar problem to what you've got in your tutorial homework. Kind of the same. You've got a ring there, and it's in a uniform magnetic field. By uniform, I mean everywhere in space it's the same value. But it's not a constant magnetic field. It doesn't stay the same value as Mickey ticks forward. It gets smaller, weaker, as time goes on. The question is, what direction will the induced current be in that loop? Now, this is a case where the other two methods, either using the right-hand rule number 1 or this idea of conserving energy, will not work. I have to use that third method. With your neighbor really quick, does the induced current come down the front of that ring or go up the front of that ring? Talk to your neighbor. Okay, folks, is it gonna come down the front of the ring or go up the front of the ring? Those who say it comes down the front of the ring, goes up the front of the ring. Excellent, excellent. Okay, which kind of makes you worried, doesn't it? Okay, I start out with a lot of flux to the right. As the magnetic field gets weaker, that gets shorter. The change that I have to add to the long vector to turn it into the short vector is to the left. That means the induced flux has to be in the opposite of the change, namely to the right. That means that induced current has to come down the front. Okay? Now, we'll do that sample question next day. I want to get to this demo because we are going to hit the ceiling here. What I've got is an iron core with a solenoid wrapped around it. And that solenoid has no current flowing through it until I hit that switch, assuming it's plugged in, and it is. Now that means, this is a soft iron core, that means that this has no magnetic field when I'm not pushing the button, and a strong magnetic field when I do push the button. And what we find is nothing. Oh, I got it. Never mind. Ah, that's what I'm talking about. Okay? Now, what's happening here? I'm going, let's say that when I hit that button, I change from no field to a magnetic field lines going up. Okay? Through this loop, I'm going from no field lines to a whole bunch of field lines going up. How am I going to fight that change? By sending induced field lines down. That means that suddenly there's going to be an induced current around this ring, turning it into a little magnet. I'm essentially ending up with a north pole against a north pole, and they repel each other. Another way of looking at it is, I want to fight that change, the change being suddenly there's a lot of magnetic field lines going through my loop. How do I fight that change? I go somewhere where there aren't a lot of magnetic field lines, namely up there. Now, I can make that jump higher by getting a larger induced current to flow through the loop. The way I get a bigger current to flow through the loop is to make it easier for current to flow in this loop. I would take that loop and make it colder by dropping it in liquid nitrogen. Now, while that's cooling down, we've still got a minute, I have another ring here that has a slice out of it. Just a little saw came and sliced it. And what you see, nothing. Okay, here's one without a slice out of it, and it jumps. Let's see. That's a smaller setting. Always go for the biggest setting. Okay. It's still bubbling in there. It hasn't quite cooled down all the way. And you remember why I can put my hand in there and still use my hand? Because I'm the teacher. Okay? Listen. It just stopped. That means it's now the same temperature as liquid nitrogen, which is the temperature of Haver. Okay. Ah, I told you I'd hit it. Now notice it didn't go up as high that time. That's because my hands got cold and it got warm. I'm warming it up, so I would jump higher and it would jump lower. Okay. Okay, that's enough for today, folks. Get out of here.